Hi everyone, my name is Abdullah. I'm from the Hasselblattner Institute, and today I'm going to talk about FastForce. Let's look at an example case. Here we have a laser cut wheelbarrow. Now when I try to lift it up, the handles break off. FastForce identifies this problem during the modeling process and generates appropriate reinforcements. And now the handles are 45 times stronger. Recently, a good amount of progress has been made around laser cutting systems that allow users to model in 3D, such as FlatFab or, as we see here, Cube. The key benefit of Cube is that it's designed to create things that are very, very strong. And it achieves that by making models based on what we call closed box structures, which are held together by finger joints. This is all good and fine, but as it turns out, some models require additional reinforcement. For example, in the case of this chair, the legs can be ripped out. So when we did the Cube paper, we already acknowledged this and added a manual reinforcement tool. In this case, you need to understand that the legs will rip out and then use the tool to add an additional plate. Now the big challenge is, and that's what my work today is about, can users recognize the problem? We also did a small study during a workshop in which we asked people to design guitar stands. And as it turns out, 6 out of 7 participants had produced their structural issues without recognizing them. So as a result, we say that the main requirement of our work is that reinforcement should not be done by the users because they just don't know how to do it. It should be done automatically by the system. And as a second requirement, this should happen at interactive rates. And here's why. I'm thinking about 2 guitar stands. I really like the one on the left, but I'm unsure about the sturdiness of the design. But with the right one, I'm more confident. Since I'm unsure while designing, I would end up iterating on both designs. But if I knew right away that both designs work out, it allows me to choose the model I prefer immediately rather than working on some backup model. So to find these structural issues, we first tried the go-to technique, finite element analysis. And we got some results. For example, we now know that at 10 newtons, the handles start to break. But the problem is that finite element analysis, in case of the wheelbarrow, took 8 hours, which fails our second requirement. When we classified all the issues that finite elements identified, we found that not all cases are equally important. Some of these only break under very high forces, but what we're really interested in is a subclass of problems that break way earlier. So we approached the problem in 3 steps. First, we manually classified the points of failure. Here's a simplification of the wheelbarrow handles. We call this case E1 because it's an extrusion connected to one side. And if you can bend it in the indicated direction, it will break. And there are other cases. Here the extrusion is connected from 2 sides, or it is completely disconnected. The important thing is that all of these points of failure fall into the category of extrusions that can be broken, or in the opposite form, cavities that can be pushed in. Number 2, we devised multiple ways to reinforce all the points of failure. For example, in this case, to reinforce this point of failure, we need to have at least 2 parallel plates connecting the extrusion, because that's what makes it structurally strong. And number 3, we wrote a software algorithm, FastForce, that both identifies these points of failure and reinforces them in real time. FastForce uses a graph representation to look for connectivity problems. First, it removes all the joints where tension can be applied. This results in disconnected subgraphs, which point to parts in the object which can fall apart very easily. Next, we look for weakly connected parts in the model by performing node cuts. Here, a 1 node cut indicates that the handles can rip off, while a 2 node cut tells us that the legs can break. After identifying all the issues, FastForce reinforces them, starting with the weakest points of failure. To stop the tray from falling in, the bottom plate is extended and anchored into the sides of the wheelbarrow. To stop the legs from being pulled out, FastForce chooses 2 parallel plates and extends them into the body. The handles and the back legs are reinforced in a similar way. We also tested the structural strength of the points of failure, and we measured the 3 to 50 time gains in strength. We also looked at the performance of our system, and we see that even with complex models which have a reasonable number of nodes, FastForce can provide analysis at interactive rates. Based on these results, we integrated FastForce into an interactive editor. Here we see the user modeling the wheelbarrow in Cube. And as you can see, as soon as a weakness appears during modeling, FastForce immediately generates a reinforcement. And this continues during the course of the modeling process. The main takeaway is that with manual reinforcement, we limit laser cutting to people with knowledge of structural engineering. But with our system, FastForce, since it has automatic reinforcement, we can bring laser cutting to people without a background in structural engineering and enable them to create sturdy objects. Thank you for your time, and I look forward to your questions.